Great, yes. I've got the unenviable task of trying to teach you assembly language in 10 minutes, so this will be quite interesting. Quick introduction, I'll run through this quickly. I'm not very interesting, the technology is more interesting, but what do? I run a company specializing in software-based encoding and decoding for traditional broadcasting, sports news, etc. But the interesting part is we build everything in-house from hardware, firmware, device drivers, high-speed electronics, software, not to be confused with the other OBS. And notably, me and my team have written assembly in FFmpeg, but also as part of our day jobs, and it's a pretty important part of what we do. So what is assembly language? Assembly language is a low-level, close to the hardware programming language. So you can see behind me, x86 assembly language. This, broadly speaking, is backwards compatible to the original 8088 CPU from 1972. And languages that we know, like C, are compiled into assembly language, broadly speaking. But this is all binary data, so how do humans read it? Well, we use things called mnemonics, and you can see those on the left, mov-l, add-l. These are basically human-readable versions of machine code. So this field is quite jargon-heavy, and as some of you know, I'm quite keen on reducing jargon. I'll try and keep it to a minimum. I would bear in mind that high school students have written assembly code in FFmpeg, so this is an approachable topic once you kind of get past the jargon itself. Why does this matter? Well, single instruction, multiple data, SIMD, or vector assembly functions really are the backbone of our industry. And quick jargon point, I'll use the terms, when you'll see the term SIMD, assembly language, vector functions, be used interchangeably. They all mean the same thing, broadly speaking. And these functions are 10 to 20x speed improvements. That's not a percentage sign. And this is a key reason that lots of the work that we do today is possible. How do we decode video in real time? How do we encode video in real time? How do we run encode of a large plant, with a reasonable amount of CPU requirements? And what's really great about this Demuxed is this is not your this isn't just going to be the only presentation about assembly. I think it's a bit like your COVID shot. You get a first dose from me, and then you get a second dose from Ronald. So Ronald's going to be talking a lot more about the detail of low-level wizardry in David, probably one of the most heavily optimized programs on the face of the planet, more assembly than actual C code. It's worth pointing out, FFmpeg and x264 assembly functions are some of the most used functions in the cloud themselves. So if you could run a sort of profiler of all the functions that operate in the cloud, you probably would find some of the types of assembly functions I'm talking about today, because video is such a heavy part of the cloud. But there is a problem, and that's kind of one of the reasons I'm here today is, well, fewer and fewer people are writing assembly, and that's a problem. You can look at, for example, COBOL. During the pandemic, the payments of coronavirus aid weren't able to be made because there weren't enough programmers who knew the language that the payroll system was built in. Now, I won't say the assembly language shortage is as bad as this, but there comes a point when these skills go away. They go away forever. So let's get into the concepts. First main concept, CPUs don't operate directly on memory. You load data to and from memory into what are known as registers, and then you do your operations, addition, multiplication, whatever, and then you move them back. You store them. And for the purpose of this, we'll look at two types of registers. Scalar registers, also known as general purpose registers. They operate on one element at a time. So you can see A plus B in that single register. But in contrast, SIMD registers, vector registers, operate on multiple elements with a single instruction. So you could add all of these elements together, so A plus B, C plus D, E plus F, all with a single instruction. And these, as you might have guessed, make it very suitable for the kind of 2D images that we work with, which means you can operate on multiple pixels in one go. Let's look at some of the other important concepts in multimedia. Shuffles, also known as permutes. They're the most important instruction in multimedia. So if you have all these elements in a vector register, what you're able to do with instructions like pshuffb is shuffle them all around and even zero some of them out. So you can see all these elements have been shuffled around depending on the index that you give to pshuffb. And I'll show an example of that in a second. It's worth pointing out that most assembly in multimedia is integer-based, and that's sort of in contrast to things like academia or fluid dynamics, where they're using floats. Intel x86 has a myriad of instructions tons and tons of them. That's, I think it's a 1,000-page book or something like that. And many are super specialist, especially the encryption ones. You've really, probably a handful of people in the world who can really explain to you what some of the encryption-related functions do, or instructions do. It's worth saying not all CPUs are capable of every instruction. New instruction sets are added, and actually from time to time removed, which is super controversial from time to time. And Ronald will be going a lot more into this, but there are examples of which are SSE2, SSE3, AVX2, and you'll see Ronald talk a lot more about those. So let's start with a simple assembly function. This is the famous zigzag. So this converts a 2D array to a 1D array. So this is post DCT, where you have larger coefficients towards the beginning. And you can do this very simply, and I won't. This is a simple example. So if you look at the zigzag, you'll see that it's trying to rearrange coefficients in a way that biases towards the larger coefficients that will be at the beginning. And this is explained very well, I would point out, in the Richardson textbook, the H.264 Advanced Video Compression Standard. I suspect it's where the book that taught quite a few people in this room is very approachable, very limited on, there's very limited background knowledge needed. It's very approachable, and I would suggest that's a good place to start learning about these things. So you can see you do a load, you do a permute. Unfortunately, I haven't got time to try and explain pointers, but for those who are familiar with C, the square brackets mean read from memory, aka dereferencing a pointer. So that means read from memory, permute, and then load, permute, and then store back. And that's one of the simplest assembly functions you're going to find. So let's talk about a few other things before we go and learn how to write one. Intrinsic, so you hear this a lot. It's being used quite a bit. These are abstractions around assembly language. Quite controversial, probably around 15% slower than assembly itself. There's plenty of people on Reddit and Hacker News who will argue with you otherwise. You're more than welcome to disagree with me and write that, but like many people on Reddit and Hacker News, you will continue to be wrong. Ronald will give you more examples about this afterwards. It's also worth pointing out there are some more advanced instructions that are not easily representable or representable at all in intrinsics itself. So we've just talked about instructions, simple moves, load, stores, multiply, but we've not talked about functions. How do you implement functions? Well, you use something called a calling convention, an application binary interface. So this function, do something. You basically say, put arguments in these registers, and that's what's known as a convention. So you or I agree to this. We agree on this depending on the OS. But as Ronald will talk about, you may want to define your own for various performance improvements. So that's one of the incredible things they do in David is actually define their own calling convention to eke out that last bit of performance. So let's write an assembly function. This is intra-prediction, for those who aren't aware. A decoder needs to go and predict the next block before applying a residual. Likewise, an encoder needs to do this prediction. This is not to scale, but the encoder and decoder's job is to estimate what that region would be. Various different ways of doing it, again from Richardson, can take pixel data vertically, horizontally, DC, which is a fancy word for average, or plane. So the goal of this is to replicate all of the pixels on the left across the entire 8x8 block. And so let's talk more about the loop structure first. So this function is, broadly speaking, a for loop. So let's talk about the actual setup of the for loop first. So you define a function, and so C global pred 8x8. That means I've got the function has 2 arguments, as you can see at the top, 3 GPRs in use. So the third GPR is there for your loop counter, so that's your for I. So you need to actually go and define that. You set that up, and let's skip the middle bit for a second and go to the bottom where you decrement the loop counter. And the key part is jump if you're greater than 0. So that means that this loop will keep going until register R2D is 0. So in this case, it will iterate 4 times. We'll talk about why it's 4 in a second. So let's look at the nuts and bolts of it. The InitXMM means you're loading 16-byte XMM registers on an SSE2 instruction set. So that's relatively old now. So what you end up doing is you want to load from the left of the picture. And what you end up doing is read 8 bytes, so 4 16-bit words to the left. You load that in such a way that A is the 4th one across. You then shuffle. You do a low shuffle such that you can replicate A across the lower half of the register. And then you do a trick, what's known as an unpack and interleave. So this is the word it's always gobbledygook in my head when I try and read it out. So I won't even try and come up with a way of pronouncing it, because I don't think there is a good one. But basically, this is a trick where you interleave a register with itself such that you can replicate A, in this case, across all the different elements. And then after that, you can write the register data back to memory and store it. And then in this case, you increment the memory location by 2 lines. So LEA is a bit of a trick to move down by 2. Because in this case, the author's done something a little bit special. A bit like in C or other languages, what they've done is they've decided to do loop unrolling. So they're actually operating on 2 lines at a given time. And they've most likely gone and measured that and decided that that's faster than doing it 1 by 1. And then to leave your function, you type ret. So that exits the function and goes back to the calling code. And there's actually quite a bit of magic that goes on underneath to go and figure out which operating system you're on, whether you're on Windows, Linux, etc. But the fact is, this is a relatively small and simple function. So we have a test suite known as checkASM that verifies correctness and runs benchmarks. I won't pretend that this very simple function is sort of miraculously fast, but it's about 2 times faster than C, which is nice. But let's look at some more interesting stuff from the real world. This is the pixel packing function that we use to get from software to our hardware. So we need to pack 10-bit data. So you can see this is remarkable. It's 62 times faster than C to write it in handwritten assembly. And I'm always in awe by this. From time to time, I run checkASM just to see how fast it is. And it really is one of the most rewarding parts of writing assembly is seeing that speed boost. Because that's phenomenal, man. Imagine 62 servers going down to 1. That's sort of analogous to that speed increase that you have. It allows for so much more. So, conclusions. Assembly functions are an important part of making encoding or decoding, say, real-time or cost-effective. And it's doable by high schoolers. And there's an ability to get massive, massive speed gains. But we have a problem, because if this expertise goes away, it goes away forever. If these engineers decide to go to ML or to self-driving cars or whatever, we're not getting them back as a community, and we will suffer in terms of cost and CPU, green, etc. So there's a lot more that we need to do to try and encourage people to write assembly. And I've only talked about x86, but there's other platforms now which are hot, like ARM and RISC-V, again, with their own assembly language. So plenty more gains like this and associated dopamine rush when you go and write code like this. And that's it.